I'm putting my answer up here just for the purpose of the video, but I do want to look at the boards. And when I look across here, I see that everybody did the first part correctly, solving for the POH and then using that POH is equal, the POH is equal to PKB plus the log of BH plus over B. And when you solve this by subtracting and getting a negative 2.24, 10 to the negative 2.24 gives you 0.0058 as your ratio, 0.0058 to 1. Now, that is a really small number, and that is because you have a difference that's greater than 1 pH unit. So several people asked about that, and when you look at this, I chose this on purpose to show you what would happen. So when we subtract 2.5 minus 4.74, these are more than 1 pH unit apart, and that's why you get this really weird ratio. So now when you get this weird ratio, you have the obvious choice was 0.0058 molar for the salt and 1 molar for the base. And for those who chose ammonium chloride, we're weighing out, this group said they're weighing out 0.62 grams to 34 grams? And that's quite different. When you think about this, you kind of want close to the same amounts there. So they picked the same thing, 0.6 grams and 34 grams. Did we have somebody choose a different salt? No, it looked like everybody chose the same salt.
I did ammonium nitrate.
You did?
I did.
Not on the board, though.
No, I didn't write the board.
No, not on the board. And so here we've got 0.592. I think that's just a rounding thing. But you can see that you have a significant difference in what you're weighing out. Now think about 0.62 grams of that salt. Is that going to have very much buffering capacity? No. So since the ammonium will allow you to neutralize hydroxide, you're not going to be able to put very much hydroxide in this buffer without seeing a significant shift in pH. So I use this one especially just to show you what happens when you have something different than that 1 pH unit. You start getting really weird numbers. All right, so we can also use this to find the pH of a buffer solution that is a basic buffer. We can do this the same way we did before. We know that POH is equal to PKB plus the log of our salt, the BH plus, well, it's actually our conjugate acid of the weak base, over B concentration. So now we can plug in the numbers. What's the pH of a buffer? If we have 0.1 molar ammonia, that's our base, and 0.05 molar ammonium chloride. That's our protonated base, or our BH plus. And remember, you have to think about the salt and know, do you have the same concentration of the ion as the salt, or is it maybe 2 to 1 or 3 to 1? That was something a lot of people missed on that last quiz with the citrate, the calcium citrate. So my POH is what I'll be solving for. It's equal to PKB for ammonia, which is 4.74, plus the log of the ammonium concentration, 0.050 molar, divided by the ammonia concentration, 0.10 molar. So that's equal to 4.74 plus the log of 0.50. So the POH is equal to 4.74 plus a negative 0.30, and that's equal to 4.44. Now, the most common mistake I usually see is when people forget to switch POH to pH. So now the pH is PKW, which is 14, minus 4.44, and that's equal to 9.56. And this is what you would expect because it's a base. You would expect the pH to be higher than 7. So we want to start thinking about what would I expect the pH to be before you do any math. And if you stop and your answer is 4.44 and you stop there, you better tell yourself something's wrong. This is a base. Goes back to thinking about what's in my beaker. Acids should be less than 7. Bases should be more than 7. Okay, any questions on the Henderson-Hasselbalch equation? I didn't have you practice one of those for finding pH because I think it's pretty straightforward with the math, and we used the equation to find the ratio, which is much harder. Okay,